Okay, good evening and welcome to our last Ask a Physicist of the semester. Tonight we do not have a specific topic that will be addressed. Our physicist will spend the entire hour answering all of your questions, or as many as they can. We have had some questions already submitted in advance, but you can also ask them through the Q&A feature within Zoom. Our physicists tonight are Paul Davies, a Regents Professor of Physics and Director of the Beyond Center, who is hosting this Ask a Physicist series. He works in cosmology, quantum physics, and astrobiology. He is the author of 32 books, the most recent of which was The Demon and the Machine, about the science of living matter. We also have Parikh. He is a theoretical physicist, and he works on black holes and quantum gravity. And Sara, an astrobiologist and theoretical physicist interested in the origin of life and how to find life on other worlds. She is also our deputy director here at the Beyond Center. So here is our first question. Why is there a tendency for the universe to get complex?
I'd like to have a go at that one because the Beyond Center had an entire workshop on that very topic. Is the universe getting more complex over time? Why and how? And will this carry on in the future? And we expected at the end of that workshop, because we had lots of distinguished scientists, to come up with a definite answer. And we didn't. So basically, the Big Bang, the state of the universe just after the Big Bang was really rather bland and uniform. There wasn't much complexity. And then over time, there's been an increase in complexity, and then leading ultimately the case of Earth to the emergence of life. And it seems to some people that life is getting more complex over time. But when you unpack all this and try to look more carefully, try to define complexity, it's far less clear as to what is going on. There seems to be an arrow of complexity increasing to the future, but if you think of the very far future, it may be that it will become simple again, and the universe dominated by dark energy. It could be that the far, far future is going to be one of simplicity. So there could be a sort of intermediate phase, which is where we're living, between a simple beginning and a simple end. But what isn't simple is coming up with any definition of complexity that encompasses all of these different things. But the short answer is, well, why is the universe more complex? It started out very smooth in the Big Bang for reasons that we really don't fully understand or agree on.
Okay. Next question. If a virus is alive, is a computer virus alive?
So I can take that one. So obviously there's a lot of debate about whether viruses are alive, so a lot of it hinges on kind of what your thinking is about what the boundaries are between non-living and living things. But one way of thinking about it is whether or not a virus is product of evolution, because that's a little bit easier to give a definitive yes/no answer to. And so obviously for real viruses, they are the product of evolution. They require some evolutionary process to be produced, which puts them on sort of the same space of evolving systems as things that we would normally agree are alive. And then you can ask the same kind of question about a computer virus, and a computer virus, for the same reason, is actually a product of evolution. It requires the evolution of advanced intelligence that can write software down and build computer programs to actually make computer viruses. So from that perspective, they're actually in sort of the same, is a product of evolution, yes, then it's a thing that can be associated to life. So that's one sort of set of arguments that are being proposed about trying to think about the nature of life. You might ask, outside of that sort of argument, just intrinsically inside the computer, is the virus alive or not? But I don't think that's actually a well-defined framing of the question in terms of actually getting a definitive yes/no answer. So if you're looking for a definitive answer, usually thinking in terms of whether it's a product of evolution or information generating it is an easier way to go.
Okay, thank you, Sara. Why is there more matter than antimatter?
Maulik, do you want to do that one?
Sure, I can take that one. So, well, right away, we're at a question whose answer isn't really known. So just to give background to people who might be wondering what the question is about, Antimatter is sort of the evil twin of matter. For every particle, such as an electron or a proton, there's supposed to be an antiparticle. And the antiparticle, in the case of the electron, is called a positron, and has almost the same properties, except it has the same mass, but it has the opposite charge. And when the antiparticle, the positron, and the electron come together, they annihilate. They destroy each other in bursts of energy. And the opposite is also true. They are formed in pairs. So they're formed in pairs and they die in pairs. So you would wonder from that point of view, why is it the case that that's what motivates the question? Why is there that we see all this matter around us and no antimatter? The answer seems to be that so there are certain symmetries in nature. We know that we believe that there's a kind of a symmetry between left and right and forward and backward in time, and also between matter and antimatter. And at first it was thought that all of these were separately true, but now we realize that there isn't exactly an equality between matter and antimatter. And there are certain forces that seem to break that symmetry. And if that's the case, then in the early universe, perhaps just slightly more matter than antimatter was created. We call it, and then all the remaining antimatter destroyed with the matter, and there was a little bit of a surplus of matter left, and that's the universe that we see around us. We're just a little bit that didn't quite cancel.
Okay, and what happened the day before the Big Bang?
It was a Wednesday, I think.
I think we probably all have something to say on that. Shall I just say very briefly that when I was a student, I always resort to that. It was believed that the Big Bang was the origin of space and time, that there was nothing before it. And so there was no day before, nor even 1 second before. And that remained fashionable for a while. But then along came something called eternal inflation. And we've actually had a question on that. Is it taken seriously? Yes, it is. The pendulum has swung. And now I think most of my colleagues think that the Big Bang wasn't the ultimate origin of all physical things. There are many bangs scattered throughout space and time, but that the overall system is eternal. And so then the question, what happened the day or the second or the million years before the Big Bang, would have an answer. We don't know what that answer is because we don't have much information about before the Big Bang. So that's, you can have it either way. Either the Big Bang was the origin of time, there was no before, or there's something like eternal inflation. Did you want to add to that, either of you two?
I just wanted to point out that both of those positions are philosophical positions and not necessarily scientific ones, because these ideas aren't at the stage of being testable. So even when people are talking about these eternal inflation models, they should have observational consequences to be scientific theories.
Thanks for bringing us down to earth.
Yeah, no worries. Well, I think the philosophy is really important. So I don't mean that as a denigration at all. That's critically important, and philosophy is really important for understanding science, obviously. But just want to point that out.
Well, I'm not sure I agree with that. Just to be
No, that's good.
There are things that we may not be able to directly test, but if there are definitely predictions of our theories, for example, the fact that there are singularities inside black holes, then we can be reasonably sure of them. But I agree with you that the eternal inflation is not at that stage yet, and it's not clear how it's a potential prediction of a theory, but it's not yet on the kind of firm ground that we can be sure that that's what happened before the Big Bang.
Could I throw in a little postscript remark for those of our audience who are totally baffled by this entire discussion? Because people will often say, well, something must have happened before the Big Bang. What does it mean to say that it was the beginning of time? But actually, that's a very old concept. And St. Augustine of Hippo said in the 5th century that the world was made with time and not in time. So it's an idea that's been around for quite a long time.
Yes.
And another quote I like to say is that asking what happened before the Big Bang is like asking what lies north of the North Pole. This was Stephen Hawking's way of putting it. And the answer is, of course, nothing, not because there's a land of nothing north of the North Pole, but there ain't no such place as north of the North Pole. And in the same reasoning, there ain't no such time as before the Big Bang.
I thought you were going to come up with a different quote from Augustine, which was in response to the question, what was God creating before heaven and earth?
Ah, yes.
He was creating hell for people who ask such questions.
It's always good to throw that in as well, yes.
Okay. Is it possible to harness energy from the quantum virtual particles that pop in and out of existence? They do have a measurable effect on on ordinary matter. Do they?
I've got something I could say on this, but I don't want to do all the talking here. Because I've been plagued by this subject for decades, because I did some work back in the 1970s that people think opens the way to harnessing the quantum vacuum. And wouldn't it be great if you could build a spaceship that could just sort of run on the energy of empty space? But it's as futile as trying to run a ship on the heat of the ocean. You've got to have a gradient. You've got to have somewhere with lower energy to extract energy. And if the energy of empty space or the quantum vacuum is the same everywhere, you can't harness it. You can't tap into it. But Maulik, do you have something you?
Yes, I mean, energy is usually conserved, and because it's conserved, there's no real free lunch available in terms of if it's a vacuum, so that there's no net energy or zero energy, and then suddenly two particles pop into existence, two virtual particles, well, they have to disappear pretty quickly, otherwise you'd have violated the conservation of energy. However, there are certain situations, like just outside black holes, where one of them can become real. That's what's called Hawking radiation, but that always comes at a price. There's some energy balance. In that case, in that example, the black hole shrinks in mass. So virtual particles can't really be used, but if they are in the presence of a black hole, they can. Or some energy gradient, as Paul put it.
Okay, we're going to take a question from the audience. From a universal, extra universal standpoint, does time exist, or would all events appear to happen simultaneously?
Right, we should let Sara do that one.
About the existence of time. Didn't you literally write the book on that, Paul?
I'm doing too much talking.
Well, okay, I think you should take that one first, because you are a world expert on it, and then I can add things if I have.
Yeah. Well, it's often said that time is an illusion or something like that. I've never had very much sympathy for that point of view. I don't think time is an illusion. I think the flow of time is an illusion, and I think we've tackled this topic in one of the earlier Ask a Physicist episodes. There are intervals of time. They're measured by things called clocks, and I think those intervals of time are real. But ever since Einstein, we've realized that time and space have to be joined together into a four-dimensional space-time, and that the way physicists think about the world, it's often called the block universe. It's just there. Just like the landscape is before you, all there at once, so the timescape is before you, all there at once. And although we individually may have the illusion that we're sort of flowing through time, or time is flowing, or we're sort of hopping from moment to moment, you stand outside all of this and look at it, there's just space-time. It's just a four-dimensional thing. It's there, part of physics, part of the universe. Nothing happens to it. It doesn't pass. Time doesn't pass.
Sara, did you want to add anything?
But just that I think biology brings in some interesting concepts of time that aren't necessarily intrinsic in physics. So Paul was talking about this arrow of increasing complexity before, and biology seems to have a directionality in time, not in the flow of time, as Paul was saying, but maybe in the ordering of events that can happen in the world. That might have some interesting connections between what life is and how it's structured across time. But that gets into some deeper ideas that are kind of on the forefront of knowledge right now. But I think Paul covered most of the standard physics perceptions of it.
Okay, then we'll move on to the next question. If there is a graviton, why is it so tricky to find? And related to that is, why is gravity so much weaker than any of the other forces?
maybe I can try that given that I'm actively involved in searching for gravitons. So the graviton is a hypothetical particle that is supposed to transmit the force of gravity. So all in the modern view, the quantum mechanical view about forces is that every force actually has a carrier, a force carrier. So the electromagnetic force is carried by photons, and the gravitational force is supposed to be carried by these particles called gravitons, which we have never seen. So just as electromagnetic waves, which are light waves, are made up of these photons, we assume that these gravitational waves must be made up of gravitons. And you can ask, why are they so difficult to find? Well, try to think about how hard it is to detect individual photons, that light is made up of individual photons. It's possible to do that. If you look in a very low light photography, you see certain graininess sometimes, and that has to do with the discreteness of photons. But so similarly, we would need very low numbers of gravity. We'd need like a very, very weak gravitational wave to make up, to distinguish, to discern the gravitons that make it up. But right now we can barely detect the gravitational waves that are coming from the collision of giant black holes. So we're a long way from detecting that.
Maulik,
Question about
why is it so weak? Do you have a position on
the
that?
other question about why is it so weak? Well, initially, all the forces are supposed to be one force. Then the different forces so the strength of forces actually isn't something that's fixed, but depends on the energy scale. So the more energetic you probe the forces, the more they behave, the more differently their interaction is. So in the case of gravity, the strength of gravity actually increases with the more energetically you probe it. And at some very high energy, which is roughly the energy of string theory, all the forces become one. So the reason we are seeing a weak gravitational force roughly is because we're probing it at very low energies.
Okay. Why do things in space spin?
I reckon that's one for Sara. You're in the School of Earth and Space Exploration. So why do all the things you study spin?
Usually because they have some momentum left over from some collision or other thing they were involved in, but also from the formation of the solar system, which, was actually had angular momentum associated. It gets imparted on the motion of the planets as they're forming, and then they maintain that spin.
And just like a dancer or an ice skater who draws their hands in will start spinning faster to conserve angular momentum as the dust cloud that forms this solar system condenses it.
And I reckon the image behind Maulik makes the point very well, because all these sort of blobs of gas and, it looks turbulent, it looks a little bit chaotic. And when gravity acts on these things, they're never going to be precisely aligned. You're always going to have things coming and passing each other and generating vorticity and so on. It would be almost the only way to totally eliminate it would be if the Big Bang was precisely smooth, infinitely smooth.
So the real question you want to ask is, why is that thing not spinning? That would be the interesting case.
Yes, if you find something. Of course, even in our solar system, there are some things that don't spin very fast. I think Venus, doesn't it spin backwards once a year or something? I know it doesn't have much rotation.
On its side because of a collision, so it's spinning.
Yes. But once something's spinning, it's hard to stop it.
Indeed.
Okay, so we have two questions from the audience that have the same subject, so I'm going to ask both of them at the same time. Was there a biggest bang in origin to the internal inflation multiverse? And is the hypothesis, is the hypothesis of internal inflation taken seriously? How does internal inflation lead to multiverse?
Yeah, I dealt briefly earlier saying, yes, many of my colleagues really do take internal inflation seriously, and there are many bangs scattered throughout space and time. So you get a multiverse, because if the Big Bang was a natural event, it could surely happen more than once, and indeed happen an infinite number of times. So the sort of general reasoning that there's a multiverse is that the origin of our universe was just a natural event, and therefore will have happened many other times throughout space and time. That's how that works. There's a related question that came in: where does the matter come from in the Big Bang? And I think we can deal with that very easily, because it's not hard to make matter. It's done all the time. For example, in particle accelerators, like the famous Large Hadron Collider at CERN, beams of counter-rotating protons moving close to the speed of light are directed together. They smash into each other. Protons collide. They make whole showers of new particles. So you can make matter in a fairly straightforward way. You just need enough energy. And remember, E equals mc squared. That tells you how much energy. So if you tell me the particle you want to make, I can tell you how much energy it takes to make it. There's not a problem, except as Maulik pointed out, whenever you make matter, you also make an equivalent amount of antimatter. And so something, when the matter got made in the Big Bang, there's plenty of energy around then something must have broken that symmetry.
Is there anything about the properties of dark matter or dark energy that would make observation possible by the human senses, either the common five, touch, taste, smell, sight, sound, or extrasensory perception or intuition, feelings, and emotion?
I can take that. So the question, I'll rephrase it a little bit. So the question about how we perceive the world, we normally perceive the world outside with our senses, but with using physics, we can sort of enhance what we mean by the senses. And the most recent example of that is the discovery of gravitational waves. So gravitational waves are really a kind of new sense for us, because although we don't directly have them in our bodies, have that sensory perception in our bodies, we can use our instruments to detect gravitational waves. And what gravitational waves are ripples in space. Basically space is stretching and squeezing. And when we become aware of those, just as when we become aware of sound waves, we experience a universe that's completely different from, that wouldn't be revealed if we didn't have that particular sense. And that sense of gravitational waves is actually sensitive to everything in the universe, because everything that has energy interacts with gravity. So in particular, it would be sensitive to dark matter also, and dark energy.
So I just want to add I like Maulik's description a lot, and in particular that he said that, the gravitational wave detectors are somehow enhancing our senses, because a lot of we have certain measuring devices that are given to us by evolution, which are our senses. But a lot of what we've done through sort of the evolution of our technology as a species is develop measuring devices that allow us to see the world in new ways, from telescopes to microscopes to gravitational wave detectors. So you can think of them just the way that Maulik described, as enhancing our senses, because they allow us to see parts of reality that aren't directly perceptible to us, but to translate that through the machines that we build into ways that our senses can actually perceive them.
I might just say, if a person could detect dark matter, then they would become very rich very soon, because there's a lot of money being spent on searching for dark matters and dark matter detectors.
Right.
All right, this is another audience question. I recently watched the movie Alien, and I was wondering about how life might begin to live on other planets that are vastly different than Earth. I've heard that humans are carbon-based life, but is there a possibility that there is life based on other elements?
Yeah, I can take this one. So the first part about whether there are environments beyond Earth that might be suitable for humans, that's certainly not the case in our solar system. So most of the bodies in our solar system would be very hostile to humans living there. Mars is probably the closest, which is one of the reasons that we're so excited about trying to send astronauts there in the future. But even there, they would need an incredible amount of life support to actually be able to survive on Mars. When we're thinking about exoplanets, which are planets around other stars, this is one of the reasons that people are very excited about the idea of looking for a quote unquote Earth twin, or an Earth-like planet, because they want to try to find environments that could potentially be conducive to life like on Earth. But the kinds of conditions that they're actually looking for are also ones that would be conducive to potentially human life on those planets. As far as the second part of the question, whether life could persist with different elements, we don't know the answer to that. There's a lot of speculation in the idea of replacing carbon with silicon. So in this idea of non-carbon based life that was mentioned, obviously all the chemistry that we have in our biochemistry is based on carbon as being a central element. You can replace that with silicon and potentially have some interesting materials. That's very speculative, and that kind of biochemistry would have to exist in a very cold environment, so it would be very different than us. There are also a lot of other ideas about substituting other elements. Probably the most famous case that's come up in the media in recent years was one that Paul was actually involved in, with whether arsenic could be substituted for phosphorus, because phosphorus is a bioessential element that's very important in the structure of our DNA and lots of other biochemistry. That's one of the reasons arsenic's poisonous for us, but there was some speculation that maybe organisms could replace arsenic for phosphorus. So you could take any of the elements that life uses in the periodic table and ask what kind of substitutions there could be, and people play these games, but the truth is we just don't know what other kind of biochemistry is possible. And then for the last part of the question, there's a lot of questions in that question. As far as whether human life could live elsewhere, people have certainly been talking about terraforming for quite a long time. So if we go back to the idea of sending humans to Mars, but that's also, a lot of ideas have been cast around, but it's not exactly clear how to do that. And there's also the idea of if you wanted humans to be around in the space environment for long term, that some genetic engineering or synthetic biology is going to be necessary to make that happen, because we're not really adapted for space environments. So that's a short answer. Paul, you probably want to add on to some of that, I'm sure, but that was a lot to get through. Sure.
No, I think you covered that very well.
Yeah.
Okay. How are we to think about information in the way physicists use the word? To me, it seems like information is the linking of concepts to matter, but that seems rather subjective.
I'm happy to have a go at that, because it was the key subject of my last book, The Demon in the Machine. The plug. Yes, it's true that information is one of those concepts that comes from sort of daily discourse that has been incorporated into science and defined there rather carefully. So it does have formal definitions that they can differ a bit depending on the nature of the subject. Where we see information playing an absolutely critical role is in biology, because you ask a biologist what is a gene, you'll be told it's a set of instructions for a ribosome to make a protein. And so in biology, information plays a really crucial role in our understanding of the nature of living matter. Like so many things in science, it starts out somewhat informal and then becomes formalized, and usually there's some mathematics behind it. Same thing with energy. People talk about, I'm lacking in energy, or we need more energy to get this going, and so on. Well, physicists use, it's an abstract concept, but physicists define it very carefully. And then there are laws governing about how energy is converted from one form to another. So I see information as playing a similar role to that of energy, but energy's been around for longer, and the concept of information, as we presently understand it in science, really dates from the late 1940s and the work of Claude Shannon, who founded what is now known as information theory. So it's a mathematical theory of information. But in my view, in biology, we need to go much beyond Shannon's rather austere view of the nature of information. But there's it's well defined in the scientists that use it. There's another aspect of information that I don't know whether Maulik wants to comment on this, about whether information is lost down a black hole. Anything falls into a black hole is black. You can't see what's inside. It's sort of lost to the outside world. So any information that throw encyclopedia into a black hole, it's lost for good. But then the black hole evaporates eventually, but emits heat and fades away. Does that information somehow sneak back out? Or is it somehow ultimately lost from the entire universe?
Yes, and so this question about information in black holes was also originally meant in a sort of casual use of the word. We just meant by information whatever described the stuff that had fallen into the black hole. Could it ever be recovered? Could we know whether the black hole had had eaten a blue chair or a red chair? But now there's a much more precise meaning of it. And again, it's through ideas like the von Neumann entropy of, we have this, an increasingly precise picture of what happens inside in the quantum gravity of black holes that involves quantum mechanical states for which we can accurately define things like entanglement, entropy, and information. So it's there, and a lot of concepts from computer science have actually made their way into physics.
Okay. Could time travel into the past be possible?
I'll have a go at that one as well, because I wrote a whole book on this called How to Build a Time Machine. And I think the answer there is that the short answer is our best understanding of the nature of time comes from Einstein's general theory of relativity that links time with space, as I said earlier, and to gravitation. Gravitation is a warping in the geometry of space-time. And nothing in Einstein's theory forbids travel into the past. Einstein was worried about this. It lay like an inconvenient truth at the heart of the general theory of relativity for some decades, until his friend Kurt Gödel, who was a rather eccentric Austrian mathematician who, towards the end of Einstein's life, worked at the same place, at the Princeton Institute for Advanced Study. They walk home together and talk about physics. And Gödel came up with a solution of Einstein's general theory of relativity, somewhat unrealistic. It involved a rotating universe, but nevertheless demonstrated mathematically that in such a universe you could travel not only from one place in space to another, but from one point in time to another. So it would indeed be possible to loop back into the past. There have been other scenarios that would permit that within the general theory of relativity, like a wormhole in space, which would be like a stargate, a shortcut between two different points. And it's true that just within the scope of the general theory of relativity, there's nothing to prevent you traveling to the past. But now we know that the general theory of relativity is not all of physics. And there's quantum physics, and as Maulik was explaining, there are gravitons. And what we don't know is whether quantum physics might block that stargate. As Stephen Hawking conjectured something he called the chronology protection hypothesis, making the universe safe for historians equipped. And the idea would be that some other aspect of physics would prevent you from doing it, because if you can travel into the past, there's all sorts of horrendous causal loop paradoxes that are very troubling to physicists, but very entertaining for writers, authors, and filmmakers. So the reason we love time travel movies is because of that sort of tension. What if I went back and changed the past in some way?
Some years ago, some students at MIT threw a party for time travelers. And to make sure that only genuine time travelers could show up, they sent out the invitations after the party was already over.
Very good.
Okay. Why do we have deja vu?
I think that's got something to do with the two hemispheres of your brain getting out of sync, but I'm not an expert in neuroscience, except I do suffer from deja vu from time to time. It's not very pleasant. So I think it's something to do with the synchronization. So what you think, oh, this has happened to me before, but it's just that you were thinking about it a fraction of a second before, because your brain is sort of getting itself into some sort of loop. I'm sure there are neuroscientists who have a lot more to say about it than I do. Sara, do you know anything about deja vu?
No, I don't know the underlying science.
I'm sure I've heard this question before.
I know that there's some cross
I know, right? Didn't we just answer it?
I think there's some cross connections that happen with the hippocampus, which is responsible for memories. But I don't really know.
What we really need is ask a neuroscientist.
Okay. Which quantum interpretation do you find most likely? Copenhagen, many worlds, etc.
None of the above in my case, but let the others speak.
I was going to say the same, but now I'm curious why you said.
I'll go with many worlds. Look, many worlds is a crazy idea because it seems that that there are an infinite number of other worlds where every single other scenario that you could have imagined actually takes place. And in that sense, it seems very radical. But in another way, it's actually a very conservative choice because it's the only one that doesn't involve modifying Schrödinger's equation or trying to come up with a definition of what we mean by classical physics and a classical measurement. So the people who believe in many worlds say that well, they're the only ones with with a real interpretation, whereas the other ones are really many words. And so I think I'd go with, but the real question is actually not what is the interpretation of quantum mechanics, because quantum mechanics is a fundamental theory from which everything else emerges. The real question is what is the interpretation of classical mechanics? We should somehow try to figure out, starting with quantum mechanics, how it is that the world appears to have a definite reality. And that, I think, is the correct question to ask. And it's still an open problem, I think.
Well, it certainly is. I mean, there are many different, it's not just those three, many different interpretations of quantum mechanics on offer. And during my career, there's many worlds or many universes. Interpretation has gone from being regarded as a sort of cranky thing that only 2 or 3 physicists took seriously to becoming almost the party line, at least for people interested in quantum cosmology. Because if you apply quantum mechanics to the universe as a whole, you don't have an observer outside or anything like that to complete the step of changing the quantum world to the classical world. So if you just take quantum mechanics at face value, just write down the symbols and the equations, it's telling you that there's an infinite number of parallel realities. So if you don't want that, you've got to add something to quantum mechanics. So you complicate the theory. And so the many people I know are purists, and they think that they want to leave it as it is, take it at face value, and then you get all those universes. I don't agree with that personally, but it would take me too long to explain what I think.
Yeah, and I think the reason I don't want to accept any of the interpretations currently is just because it's actually related to the problem that Maulik was talking about, but just that we don't understand the physics of the observer. And a lot of the interpretations are basically based on the interaction of measuring devices or observers with quantum systems. So my perspective, which is always the perspective on everything interesting in physics, is that once we figure out physics of life, we might be able to sort out that problem. But we need to figure out what minds are, what living things are, and how they interact with the world to give definite reality, as Maulik was saying, at least in our observational experience, in order to be able to figure that out. And I don't mean that in a wishy-washy way. I mean that in a very concrete, there is missing physics related to information and what it is to copy information from one system to another, which is what a measurement is. So.
Okay. With all the data being collected every day, we have more data than we have ever had in the entire human age. How far will we go in terms of machine learning, AI, as the data we have will one day become redundant? For example, with people's habits with shopping being recorded with the apps and algorithms, will there be a time when we would have figured out and categorized all the human's traits right from when he or she is born?
True that we're drowning in data. It's particularly acute in some aspects of physics, and I apologize for coming back to physics, but this is Ask a Physicist. The World Wide Web, not many people know this, but it was invented at CERN, the particle physics lab in Switzerland, because of so much data that was coming in from these collision experiments and other experiments was needed to be disseminated so it could be analyzed properly. And that was the genesis of the World Wide Web. And that remains true, that experiments like the Large Hadron Collider, just staggering amounts of data. But it's also true in astronomy. And there's something called the Square Kilometer Array, which, as the name suggests, will have a collecting area of a square kilometer. It's a radio wavelength. So these are antennas spread out to have a total area of a square kilometer, partly in Western Australia, partly in South Africa. And the amount of data that will accumulate, I think I can't remember, but it's some staggering figure like the entire data content of the internet, every hour or something. And so the question of how it can be stored, let alone analyzed, becomes really acute. And so this is only going to increase as our instruments get more and more sensitive and we can collect more and more data. What do we do with it all, and how do we analyze it? And do we need machine intelligence or artificial intelligence to spot the patterns? Human beings are very good at spotting patterns, sometimes where they don't even exist. But when you've got staggering amounts of data, one last area that I've just thrown in for good measure is in genetic sequencing. That's generating huge amounts of data. And you take something like cancer sequencing. Are there patterns there? This whole field of bioinformatics is really, really important. But making sense of it all is another step entirely.
Okay. How far in the spectrum of sounds, different frequencies, have we heard? What did we hear? What have we not?
Different, I think.
Well, I think so. Our own ears can hear sound from 20 hertz to I think 20,000 hertz, and there are other species, of course, that have much, like whales, I think, have down to like 5 or 6 or 7 hertz, and so that corresponds to a wavelength of about 50 meters. Now, sound, of course, are vibrations of air. Or they're basically vibrations when you sort of shake something, a medium. But similar to that are gravitational waves, which are ripples of space, as we talked about earlier. And those can have much longer wavelengths. In fact, the gravitational waves that we see from the collision of black holes have wavelengths of 2,000 kilometers. So as we open our experiences or senses to these other kinds of generalized sounds, we'll see a different universe out there.
In terms of the human ear, it's really rather limited.
Yeah.
So there are certainly animals.
It's still impressive that it's some 10 orders of 10 octaves in terms of, whereas in our vision, we only have 1 octave of sight. So,
and the older you get, the worse it gets. Yeah. You miss out on certain frequencies.
Okay, in Doctor Who, there is an entity called the Great Intelligence, which is a mind without a body. Is such a being plausible in the real world?
One for Sara.
Sure. Yeah, there's a couple things interesting. I mean, so I think the first thing that comes to mind is thinking about Boltzmann brains, or this hypothetical thing in physics that a brain might spontaneously fluctuate into existence and not necessarily have a body or any evolutionary history, but could have thoughts and feelings just like you or I do. And the premise there being you could even be a Boltzmann brain right now and you would come complete with all your memories and think you were a real living brain, but not actually have a past. And so there's a lot of debate about Boltzmann brains and what their usefulness is. I don't personally think they're actually physical, based on how I think about what life is and the nature of minds. But there's also another aspect to your problem, which is just whether minds can exist without bodies. So that was, a brain without a body, but what about a mind without a body? And there's also, the whole set of ideas about minds maybe being part of some Platonic world that exists separate to physical reality, because we can't really explain sort of the mind-body duality. But I also don't find those kinds of arguments particularly constructive. So I think that minds and consciousness actually really do require physical bodies, because of the particular causal structure that they have. as physical systems, but also that they require an evolutionary history to even emerge in the universe. That's actually the part of the physics of how they get generated, just in the same sense that some particle pairs are only produced by certain interactions, and you actually have some constraints on their production. So we can think about that concretely in physics. Part of the argument that I make about living things is they don't just spontaneously fluctuate into existence like me or this cup, but they require that evolutionary process to generate them. And that's actually the physics of their generation mechanism. So those are a few perspectives on it.
Yeah, to abstract that question, if I think about just what is the most general thing that could have information in it, like a mind. In physics, the building blocks fundamentally are quantum fields or maybe even strings. And so whatever it is that you use to, but that's the same thing that stuff is made of. So you would call that body as well. So there's really no there's no real way to get mind without a body, because they're both in a way made up of.
I think at the very least, when we talk about minds, there has to be something like memory, because if it's just fleeting experiences, moment to moment, and not stitched together in some continuity, you wouldn't really want to call it a mind. You might just call it a instantaneous perception or something. But something like a mind with a memory. Memory means the information has to be stored, and it's got to be instantiated in some physical degrees of freedom. I don't see that you could have the information just sort of floating free without being connected to matter in some way.
Okay. If the universe is flat, how does it have no edge, and what is it expanding into?
Very familiar to physicists. They get asked this question all the time. Do you want to have a go at that one, Maulik?
Sure. So imagine a flat piece of paper, right? And imagine that there's a grid on this piece of paper, and with each of the little grid marks being about a centimeter apart or foot apart or whatever. Now, but now imagine that this paper is actually infinite. It's infinite in all directions. So it has no edge, right? Because it's infinite. And yet you can say that a little bit later, everything is expanded in the sense that each of the grid marks have gotten, which were previously a centimeter by a centimeter, are now maybe 2 centimeters apart. So in that case, you can see that space is expanding. The space between any two grid marks, grid intersection points, has gone from 1 centimeter to 2 centimeters. And yet the total area of the whole thing is infinite before, infinite later. There's no need for an edge. And it's not that it expanded into anything, it's that space stretched. So if you can conceive of an infinite universe, it's very easy to imagine it expanding without the need for an edge. Now, if you want to make it a finite universe, you can also do that. So imagine that you have a flat universe, and there's a boundary. Well, okay. So there are two ways of. You can imagine the flat universe where there's no boundary, but where one edge. If you go off in one direction, you're going to come back in another direction, and that's called a toroidal universe. And that can also expand and expand with the grid sizes increasing. But with the total number of steps before you come back the same. So the same number of grid points, but the distances within each grid, within each cell of the grid, are increasing in time. So it's not actually necessary to embed the universe into something else into which it's expanding. So that was a two-dimensional analogy. In reality, the world is three-dimensional, so you have to imagine a three-dimensional grid that's extending in all directions, in which the vertices of this grid are expanding in time.
So how do we know the piece of paper is infinite?
How do we know the piece of? We actually don't. That was an example of I wanted to give an example in which we could visualize it easily. We don't actually know whether the universe is finite or infinite. That's a very basic question about the universe that we don't know.
But I don't think we could ever know. Isn't that right, Maulik? I mean, we only ever measure finite things. So.
Yeah, I was just going to ask that. How would you even be able to say the universe is infinite? Because that's not physical.
Well, we could find out whether it's finite if we send off light.
Yes, you could falsify.
Then we'd find out. But if we send light off in one direction and it didn't come back to us from the other side, then all that could mean is that either it's infinite and it's never going to come back, or we just have to wait and wait and wait until it comes back finally. So
and there's an analogy with the Earth. You could say, well, it looks pretty flat everywhere I go. Does it go on forever and ever, or is there an edge somewhere you drop off it? And the answer is no, it's curved into the surface of a sphere. So there's no edge or boundary, but it's nevertheless finite. But if the Earth were 1 million times bigger, you might think, well, maybe it does go on. If it's 1 trillion times bigger, so the bigger the radius, the flatter the surface, and the harder it would be to determine whether it was finite or not. And we're sort of in that situation with the universe. If it is finite, it's going to be such a huge distance to go around it that we don't see any hint of it yet. But it's hard to see how we could ever rule it out, because it just might be awfully, terribly, immeasurably big, but not strictly infinite.
Well, there's an interesting. Oh yeah, go ahead.
Is it like, how would you know the difference between the universe doesn't have a size and the universe is infinite? Because I just don't see infinite as a physical thing that could actually exist. But could you?
I don't think you can, because you can only ever you can make a measurement and there'll be error bars, and you can only ever say, it looks flat and infinite to within a certain amount, but you could never pin that down to say the curvature of the universe is precisely zero and not, some tiny number.
Yeah, I guess I was asking in part, maybe it doesn't have a size.
No,
but you think it's an undefined concept or something?
It would either have a have a size, or it would be infinite. I don't think it cannot have a size.
Okay.
We might not be able to determine that size. But by the way, there's a further twist to this excellent question, which is that in many of our theories, particularly string theory, we expect that there are additional dimensions of space, and those dimensions are not in the 3 dimensions. We can't point to them because they're additional, they're extra, they're not in the 3 directions we can point to them. And those, because they remain, if they're there, where are they? And one of the things that we believe about those dimensions, which is that they're very, very small. And so those definitely are finite. And so that makes it very interesting. Then we have a question, why is it that there are these other certain dimensions that are very finite, in fact, tiny, microscopically small, and other dimensions that are enormous and maybe even infinite? And that's, again, another unsolved problem.
What Sara said actually just prompts me with a crazy thought, if we're allowed to do this towards the end of this Ask a Physicist. So we're all used to the fact that the concepts of space and time are going to break down on a very small scale, the so-called Planck scale. So you go down to that level and you really can't talk anymore clearly about space and time in the everyday sense. But could this also be true on a very large scale? Might there be, as Sara was saying, some sort of absolutely stupendously huge scale at which it no longer becomes meaningful to employ these sort of everyday concepts? A sort of duality between the very large and the very small might involve some new physics. Space-time breaks down on this big scale as well as on the small scale. I don't know.
I think it's worth thinking about. I've been thinking about whether the universe had a size a little bit lately for other reasons, but
we should get Jessica's opinion.
Yeah.
Nobody wants my opinion. We are going to start wrapping up. So depending on how long this question takes, it may be our last, but I wonder if the panelists have thought on the co-opting, for lack of a better word, of scientific concepts as they relate to spiritual or esoteric theories. Is there hope of others taking a page from the Beyond playbook and reintegrating scientific, philosophical, and theological dialogue? Is there hope of this becoming standard practice specifically in institutions of higher learning?
Yeah, we've sort of touched on this as we have gone along. I think if you're a physicist or a cosmologist, that you're dealing with these really foundational questions. You know, what is reality? What is space and time? What is consciousness? And these are questions that for thousands of years were in the province of religion and philosophy, and they're now part of science. So it's quite natural, I think, that we should revisit some of those topics. And I already mentioned one example, Augustine's proposal that the world was made with time and not in time. So I've had a very productive dialogue with theologians, scholarly theologians who are very clever people over the years, just to talk about the way they see the world and the way we see the world. And I think it can be a very good thing for students to be exposed to the history of ideas in that manner. And I've just been teaching a course at ASU on precisely that, foundational questions in science, and it often touched on theological issues. So I'm quite friendly to that idea, and that's very different from teaching a religion as this is the truth. It's simply saying, well, there's these ideas out there, history of ideas that go back in philosophy and religion, and many of them get sort of recycled in modern science. And I think that's just interesting in its own right.
A few hundred years ago, we didn't have these specialized departments of physics and chemistry and biology. In fact, science existed at the university level as part of natural philosophy. And so I think it's sort of nice that the kind of questions that we're dealing with in both physics and biology about what life is and what space and time are sort of returning to questions that may have started out in philosophy.
We do have time for another. Could someone ever devise an experiment that could make string theory falsifiable?
I think that's one for Maulik.
Sure. Well, I mean, so string theory, which was originally supposed to be a theory of everything, has been mocked a little bit because it's become a theory of anything, because there are all kinds of different worlds that are possible in string theory, and it seems almost that whatever you come up with, there's some kind of world in the multiverse of string theory that's described by that. Still, there are certain things that would falsify string theory, and the question, you know, these are pretty extreme. This is a pretty extreme example, but if we were to discover, say, more than 9 dimensions of space, then that would falsify string theory. So there are some, it's not true that there are no predictions at all, and that there are actually definite predictions. They're just very, they sound crazy, but the theory does have certain predictions. It's just that from a low energy point of view, it's not a very predictive theory yet.
Okay, maybe one more if it can be answered quickly. If objects traveling at less than the speed of light travel forward through time and tachyons would hypothetically travel backwards in time, how does time work for a beam of light?
Frozen, it stands still. So if you're a photon, you're in every place at once on your trajectory.
Well,
that was simple to answer.
No, there's no actual, it's very interesting. There's no actual passage of time for a photon in which everything happens sort of in a flash, but there is an ordering of time still. So you can say event A happened after, event B happened after event A, and event C happened after event B, and so on. But you can't, but there was no time that passed between. So there's no measure of time, but there's still a sequence.
All right, well, that brings us to the end of our Ask a Physicist for this semester. Because the series has been so successful, we plan to do it again in the fall on the last Monday of each month, probably at the same time. Make sure you're following us on social media and you're signed up for our email so you don't miss the announcements with the dates, times, and topics. Thank you so much for joining us tonight and for your questions. And we hope you enjoyed it and that you'll be back with us next semester.
Thanks, everyone.
Bye.
Bye.